Because the room is big. Now what do I have to do? Okay. All right, I think we'll get started. So it's with great pleasure that we have Michael-Dine here today for the last colloquium of the semester. Michael graduated from Johns Hopkins and went on to do his PhD work at Yale. His thesis was titled Heavy Quarks in QCD, so it's actually not so far from what you're talking about today. So you're coming around full circle. He then went on to do work at SLAC, Institute for Advanced Study at Princeton and City College of New York before going to Santa Cruz in 1990. To say that Michael's work is impactful would be a gross understatement. I looked up in Inspire today, and he has 18 papers with over 500 citations. And of those, 7 of them have over 1,000 citations. So if you're talking about impact, that's extraordinary. He's well recognized. His awards include the APS Sakurai Prize. He's a member of the American Academy of Arts and Sciences and a member of the National Academy of Science. And today is rather special because we through the Fine Theory Institute, we're awarding Michael with the Larkin Prize for theoretical physics. It's actually last year's prize. It says 2023, but we're at the end of 2024. And that,
in spring.
Yeah,
but
it was awarded in 2023.
I was awarded in 2023, right? Normally you were going to come in spring of 2024, but there's a certificate and now the hard thing. No, I'll just straight up. An award for you for the saying the Anatoly Larkin Award.
Thank you. Thank you.
So,
Thank you all.
there. And so with that, look forward to your lecture.
Thank you. All right. So thank you. It's a great honor and a privilege to be here and to receive this award. And today I'm going to talk about something that's not really in the list of things that were mentioned, something I'm thinking about now, the kind of thing that older people do is they sort of think about the great problems in physics and what they can make of them. So I'm going to ruminate on quark confinement. So if someone asks what rumination means, it sort of means thinking kind of over and over about it. So confinement of quarks is one of the great problems of theoretical physics. The quark model itself is over 60 years old, and there is strong experimental evidence that nucleons are composed of quarks tightly bound. But quarks, which should be distinguishable by their fractional electric charges, have not been observed as free particles. It was suggested that a quark-antiquark pair, for example, is bound by a potential which grows linear with their separation. As a result, as one tries to separate them, one simply produces more and more such pairs. So one just has to use more and more energy, and the more energy one provides. Oops. So if I have a heavy quark and heavy antiquark separated by some distance r, as I separate them further and further, I have to produce a linearly growing energy. So B of r goes like some constant times r. And so I have to provide more and more energy, and that energy can be converted, it gets converted into producing other particles. Okay. So over time, this has been this fact, if you like, which is a fact, has been established by expensive numerical simulations, but it is yet to be established by analytic computations or by some more conceptual method. And proving this analytically is one of the Millennium Prizes of the Clay Foundation. If you do it, you win $1 million. So what's interesting and what we've known for about the better part of 3 decades is that there has been much interest in theories with supersymmetry. Supersymmetry is a hypothetical symmetry of nature which relates bosons and fermions. Were it an exact symmetry, every fermion we know, every helicity state, the spin up or spin down of the electron, for example, would be accompanied by a corresponding boson of the same mass and similarly for a boson of the same mass and similarly for bosons. So for the particles of the standard model, the photon would be accompanied by a photino, the gluon, the carrier of the strong force, by a gluino, and quarks by squarks, and the electron by a scalar called the selectron, and so on. This proposal has the virtue, and this is one of the reasons that it initially created such interest, is it can resolve the puzzle associated with the Higgs particle in the standard model. Well, the Higgs particle seems relatively heavy at 116 GeV now we know. Its mass would more naturally seem to be much larger, easily of order of the Planck scale, the Planck mass, the scale at which one expects quantum effects to become important in gravity, or about 10 to the 19th GeV, or 10 to the 19th times the mass of the proton. This idea predicts that supersymmetry should be a broken symmetry, okay? So certainly we do not see such degeneracy, with particle masses scaling like the mass of the Higgs boson, or perhaps a bit more. Now, so far, at best, though, there's only a bit of indirect evidence for this idea, okay? And the Large Hadron Collider has searched hard for these particles and so far not found them and set limits on their existence, on their masses. But supersymmetry has been proven to be an interesting theoretical playground. So while it may not play an actual role in nature, supersymmetry provides access to questions which are difficult to approach in ordinary field theories. The symmetry is very restrictive, and it is often possible to make exact statements about these theories which would be inaccessible within, say, the standard model. Features such as masses and interactions can sometimes be determined exactly. A simple example is QCD without matter fields, with quarks. Without matter fields or quarks. This theory contains gluons and their fermionic partners, the gluinos. The gluinos are a color octet, just like the gluons are a color octet, this time of vial fermions of left-handed fermions. If we add quarks, we must also add scalar quarks or squarks. So this brings me to the fact that for this question of confinement, which is very challenging in ordinary field theories, in ordinary QCD, is accessible to supersymmetric QCD. Confinement and the existence of a mass gap are readily established features of many n=1 supersymmetric gauge theories. I introduced this term n=1. This is the smallest type of supersymmetries. N=1 counts the number of supersymmetry generators. The supersymmetry generators, because they turn boson to fermions, okay, are themselves fermionic operators. So they carry some spin index, okay, and n=1 is the smallest such possibility. Now, this is the case in particular for gauge theories without matter fields and gauge theories with only massive matter. Exploiting tools such as holomorphy, and I'll explain a little bit later what that is, it is possible to study many aspects of the problem, such as the role of monopole condensation, which is something that's believed to be important, long believed to be important in understanding confinement. I won't review it here, but chiral symmetry breaking can be readily explored in supersymmetric gauge theories, including quarks and squarks. So chiral symmetry breaking here refers to the phenomenon that in ordinary strong interactions, the pi mesons and the associated octet of scalar mesons, pseudoscalar mesons, are approximate Goldstone bosons of a spontaneously broken symmetry. Okay. In a pure supersymmetric gauge theory, for example, a theory with gluons and gluinos only, one can establish that there are magnetic monopoles, and these condense, i.e. the corresponding monopole fields have non-zero expectation values in vacuum. It follows that if one has a quark and antiquark, think of an infinitely heavy quark and antiquark like I drew here, there is a potential between them which grows linearly. The point is that due to the monopole condensation, the gauge fields are heavy, and it is energetically favored for the electric flux between them to form tubes. Okay, so normally one thinks of the flux, the electric flux. Here, let me draw it here, as being sort of Coulombic. spreading out between them. Yeah, so if I, so in this case, in the case of monopole condensation, the flux lines are tightly collimated. And the force, rather than going like 1 over r, goes like r. So in the 1990s, I said this was firmly established by Seiberg and Witten. And the analysis involved some very beautiful mathematics for which achieved wide recognition. But it's natural to ask, can one extend the understanding of confinement in supersymmetric QCD to non-supersymmetric QCD? So one could start, for example, by taking a supersymmetric gauge theory without matter and then introducing a gaugino mass term. So again, to say what I mean by that, I mean a theory which has gauge bosons, some gauge bosons, and their fermionic superpartners lambda A. So this is the theory I'm studying. The lambda A, the interactions of the lambda A are governed entirely by the gauge principle. Okay, so the question is that can we extend the result to this theory? Can we extend the result of confinement to this theory? And we're going to see that this is a non-trivial problem. Now, due to the mass gap, due to the fact that, as Seiberg and Witten showed in the supersymmetric theory, the theory has a mass gap. So there are no massless states. Adding a small mass for the gaugino confinement would be expected to persist. The question is whether there is, as you vary the gaugino mass, as we vary the mass of this particle m lambda, does confinement persist, or is there a phase transition? Is there a transition from a confining phase to a non-confining phase? Okay. Now, in this talk, I'll first address the analogous problem in CPN theories. So CPN theories are theories in 2 dimensions, which are well understood at large n, okay, which can be solved at large n. Okay. And we'll see that there is a phase transition as one passes from the supersymmetric theory, which is non-confining in this case, so it's sort of the opposite of, or possibly the opposite of the QCD case, to the non-supersymmetric theory, which is confining. Confinement is a phenomenon of the far infrared theory. And the infrared theory, so again, when we write a formula like this, okay, we're asking, does this form, we need this to hold for a large R. And that's what I'm calling the far infrared, the long distance part of the theory. Okay. So things will be, so as I say, the infrared theory is different in both limits for this 2-dimensional theory, but things will be different in 4 dimensions. Okay. Now, focusing on the heavy quark anti-quark potential related to something called a Wilson line, we can rule out a second-order deconfining transition. Okay, and we'll describe that. It is harder to rule out a first-order transition in the large, but in the limit of large n, okay, the limit of large n, which I'll also explain, the limit of large n is a limit where the number of colors, rather than being 3, is large some number n, okay, and where the coupling passes to 0 in a particular limit, okay? And we'll see that in that case, such a transition would appear to be unlikely. And it's widely believed that this large n theory resembles ordinary QCD, but again, proving that is another matter. Okay, so ruling this out would constitute a proof of confinement. So to describe a little bit what I'm going to do, I'm going to first describe confinement in supersymmetric gauge theories, just briefly. Then I'll describe these CPN models, which exhibit confinement in the non-supersymmetric limit and not in the supersymmetric theory, and what happens is what passes between them. I'll talk about the persistence of confinement with small soft breakings. This is in QCD again, in 4 dimensions. Establishing that a phase transition at large m lambdas required in the large infinite m lambdas, if the large infinite m lambda theory is to be non-confining. Arguing against a second-order transition is easy. Features of a would-be first-order transition are more challenging. At large n, I'll talk about that a little bit as well, we'll perhaps rule out the first-order transition. Okay. Then I'll talk about including light quarks, and I'll conclude. Okay, so confinement and supersymmetric gauge theories. Proving confinement in non-abelian gauge theories without supersymmetry remains, as I said, one of the great challenges of theoretical physics. What is remarkable is that with n equals 1 supersymmetry, one can establish confinement in a range of gauge theories in a variety of ways. These involve studying the form of the effective theory, which describes the system at large distances. The effective theory is highly constrained by supersymmetry. In particular, any potential for the fields in this theory must arise from an object called the superpotential, which must be an analytic, or more precisely mathematically stated holomorphic function of the underlying degrees of freedom. Okay, so this restricts a great deal the form of this effective theory, and the effective theory sort of tells you what the large distance theory looks like. Okay, so to establish confinement, okay, following Seiberg and Witten, one can prove confinement and the existence of a mass gap by exhibiting monopole condensation in theories which can be obtained by deformation of the n equals 2 theory. So I described this. So this theory I described here is a theory with n equals 1. For n equals 2, one adds a scalar field phi a, an adjoint scalar. Okay, and this describes the n equals 2 theory. Okay, so what Seiberg and Witten did is they show that in the n equals 2 theory, there exist points where monopoles will become massless. And they established that these monopoles, in fact, do become massless, and one can write an effective action for these. And starting with n equals, but another approach to this is starting with SUN supersymmetric QCD with n minus 1 massive flavors. One can compute the spectrum for small quark masses, and then using holomorphy, this analyticity I described before, one can establish that the system is gapped when one gives the quarks large masses, and again, establish confinement. So n equals 2 theories and some of their features, as to say, I described a little bit what they are. Most discussions, what you hear about in colloquia and in talks, are about center on n equals 1 supersymmetry, one set of supersymmetry generators. Theories with more supersymmetry are theoretically interesting. They're not likely to be interesting in nature, as their dynamics are highly restricted by the symmetry. A simple theory with 2 supersymmetries is a set of gauge fields, 2 sets of fermions, I should have written that, in the adjoint representation, and a scalar field in the adjoint representation. The potential for the scalar field phi has this simple form. Okay, it looks like phi dagger, TA phi. TA are the group generators. Okay. And this has the feature that there are values of phi, so values of phi in this expression, for which the potential vanishes. So for example, for an SU2 gauge group, if phi could be thought of as a matrix, it's a matrix in the adjoint representation. If it's some constant times tau3, this gives the potential equals 0. So these two v's are different. There's a lowercase v here and an uppercase v. Hopefully that's clear. In these states, this gauge group is broken to U1. There is a massless gauge boson, 2 massless fermions, and a massless scalar. The effective theory which describes these is highly restricted by the symmetry. The set of vacua labeled by Z is called the moduli, labeled by V, I'm sorry, is called the moduli space and has a generalization for larger gauge groups. Okay. So then Seiberg and Witten, as I said, deformed this n equals 2 theory to n equal to 1 with n equals 1. Okay, so what in the n equals 2 theory, they realized that there are n points in the moduli space of vacua where monopoles become massless. Okay. And these transform into one another under a Zn symmetry. So U here is trace phi squared, okay? And it's some constant times e to the 2 pi I over n. So they're n, so I should really write e to the 2 pi I k over n. Okay, so they're really n different vacui. Adding a large mass for the adjoint and for the extra fermions, the theory reduces to SUN supersymmetric QCD without matter. This theory has a Zn symmetry acting on the gluinos. So lambda goes to e to the 2 pi I over n lambda, which is known to be spontaneously broken by gaugino condensation. with lambda lambda, an expectation value for the product lambda lambda. With the large adjoint mass, Seiberg and Witten showed that there are n possible values of the magnetic field, or this magnetic condensate. The n monopole ground states correspond to the n possible values of the Gaugino condensate. So I wrote that again. This lambda lambda is e to the 2 pi I k over n. Okay, so that's a start. And as I sort of drew here, okay, monopole condensation is one picture of how confinement arises. Okay, so in fact, Seiberg and Witten were able to prove that the confinement occurs in this theory. Okay, now I'm going to take a step back and look at a two-dimensional model, which has some features in common and some which are different, but it in particular has confinement or non-confinement, depending on whether the theory is supersymmetric or not. And these models are known as the CPN models. So CPN is a particular space known in mathematics, models in 2 dimensions. So they're fields that live in 2 dimensions. Okay, so these theories are, the non-supersymmetric theories are confining and gap. That's been known for a long time, since the late 70s. What is similar to QCD is a confinement is a problem of the far infrared. So again, we can look at very arbitrarily widely separated charged particles. What is different here is that turning on supersymmetry breaking, the far infrared behavior immediately changes. The supersymmetric theory is not confining. So instead, so as I said here, for the 4-dimensional gauge theory, okay, for small values of m lambda, the theory is still confining, and I'll talk about that more as we go along. Okay, so the transition, if it occurs to a non-confining state, occurs at some finite non-zero m lambda. For the CPN theory, it occurs at 0. Okay, so it's 0 breaking of the symmetry. Okay, so it's natural, in fact, to focus on a Wilsonian action. That's an action where you integrate all the physics all the physics above some cutoff scale lambda w. Where lambda w is well below the scale of the theory lambda, the dynamically generated scale in the 2-dimensional case, or lambda QCD in the case of QCD, the QCD scale in the 4-dimensional case. The infrared theory is a pure U1 gauge theory. Confinement is a feature of this very low energy effective theory. Now, it should be noted that for heavy test particles, which are integer multiples of the basic charge, there is no linear potential, and Wilson lines do not exhibit an area law, the characteristic of confinement. But for test charges, which are fractions of the basic charge, a linear potential at arbitrarily large distances arises. Okay. Now, Witten demonstrated that the supersymmetric theory is not confining. This can be then understood in the language of the far infrared theory, which is trivial. There are no massless excitations. So I should say, first, in this case, in the CPN case, in 2 dimensions, oops. Let's see if I can. So in 2 dimensions, the propagator of 2 gauge fields, A0, let's say of x, A0 of 0, it's already linear. So the fact of confinement is almost a triviality. Okay, so the exchange between charged particles of a gauge field gives rise to a linear force. Okay, provided they're massless. So this is for massless. And what Witten showed, though, is that in the supersymmetric case, there are no massless gauge fields. So this force falls off exponentially. So this goes like e to the minus mx for non-zero mass. Okay, so this theory has a sharp change as one goes from supersymmetry to not. And I've sort of written down here for what the theory is. Okay, so in terms of it involves some scalar fields, which are here I called Ni, some fermion psi I, and some extra fields, so known as auxiliary fields. These are fields which are determined by their equations of motion, and some fermionic auxiliary fields. And I've written the Lagrangian here. There's a kinetic term, gauge invariant kinetic term for the scalars, for the fermions. And I've included a mass term for the fermions. This is the supersymmetry breaking. Okay. And there are terms for these various auxiliary fields. Okay. Okay. So for zero mass, the fields pi and a mu. So zero mass for the fermions. This is the limit that's supersymmetric. The fields pi and a mu combine to yield a massive field. For any non-zero fermion mass, the gauge boson propagator behaves in momentum space as 1 over k squared. So in coordinate space, it's linear in R. Okay. So at very large distances, the theory still confines, and a sufficiently large separation of heavy charged objects will consider a Wilsonian action with only a massless gauge field. Okay, and the potential, as I said, is linear. So let's now turn back to QCD. Let's ask about the possibility of a phase transition in supersymmetric QCD as we increase m lambda from 0. Okay, so the theory is gapped, as we said, at m lambda equals 0. So for small m lambda, okay, for small mass for these gauge fields, okay, there will be no qualitative change in the behavior of the system. It remains gapped and confined. The question then is there a phase transition at some finite value of m lambda? Now, a priori, this transition might be first or second order. Okay, in the case of second order, so second order is a case of a smooth transition. Okay, and in that case, there's a massless particle at the transition point, a massless field. Okay, the first order case is the case where you have where at some point you have two ground states of the system and they cross. Okay, they cross in energy. So we can rule out the second order possibility in more than one way. Okay, so ruling out a second order phase transition, if the transition is at some point m lambda naught, and at second order, there's a massless field at this point. But there is a theorem due to Waffe and Witten that there are no massless particles in QCD-like theories with massive constituents. Okay, so we have this massive gaugino. Okay, we want to have a massless scalar. Okay, and roughly speaking, we can think of that scalar as including this massive gaugino constituent. So that theory, that rules out this second order possibility. We can understand this another way. If we integrate out the gaugino, we obtain an effective low energy theory, which we know confines for small m lambda. This is the theory which describes the far infrared relevant to confinement. So in this theory, there is a where heavy quark and anti-quark are far separated, the energy grows. For larger m lambda, the far infrared theory in this second case would be a second order transition, would be a second order transition is the same. So the theory remains confined. So again, what I'm calling this far infrared is this very large R limit. Okay, and the theory at this very large R is the same in either case. Okay, so in the second order case. So again, there's no transition. There's no such transition. Now it's harder to rule out the possibility of a first order transition. Okay, this is the case where there are two distinct theories or two distinct vacua, which might describe the far infrared, one of them confining and one not. Okay, now as we integrate out the gluino for small gluino mass, the confining theory has lower energy. Then at some m lambda, call it m lambda naught, the two states are degenerate in energy. Okay, and for larger gluino mass, the unconfined theory has lower energy. Proving that this does or does not happen appears challenging. Note that this is different than the case of CPN in 2 dimensions. There one has one theory that is trivial in the infrared, the supersymmetric theory with a mass gap, and one which confines with a massless gauge field. That's the non-supersymmetric theory. The transition at m equals 0 is characterized by a drastic change in the infrared behavior of the theory. The case of 4 dimensions is quite different, as the transition, if it exists, must occur at non-zero value of m lambda. Still, it is not a simple matter to rule out this first order possibility. So there's a case where one can make, what seems one can make a statement, and this is the case of large n. Okay, so let me describe what large n is. Large n is an idea that was introduced by 't Hooft, and it was so. So here the n is the number of colors. Oops, number of colors. Or another number of colors carried by a fundamental quark. Okay, so the gauge group here is SUN instead of SU3. And the large n limit is defined by letting n goes to infinity. Okay, but with the coupling constant g squared n fixed. Okay, and in this case, the theory is, if one thinks about the Feynman diagrams of the theory, the Feynman diagrams are a special class known as planar diagrams. Oops. Okay, this means that they can be drawn in a plane. So if I think about, for example, the diagrams quarks Q and Q bar exchanging gluons, this diagram is planar. This diagram, the diagram where the gauge bosons exchange cross each other, is not. Okay, so this is planar. This is non-planar. So one has a subset of Feynman diagrams, and they have various properties. So you can prove certain features of prove certain features of this theory. Okay, from this. So, yeah. So here with some assumptions, we can rule out the possibility of two phases in a resulting first order transition. The basic assumptions.
We know that's not the case, right? For instance, the blue in the problem say zero in perturbation theory, but it's not zero.
Right.
Smooth and then even at large n.
Right. No, you could even go further, and you could say let's think about the Seiberg-Witten analysis with the monopoles. Okay, and the monopoles are also some non-perturbative object. So I'm being a little flip, if you like. So I said, so the monopoles are non-perturbative objects, and they're important to the confinement phenomenon. So I agree with you. It's a little misleading to say that, or at least confusing in what sense the theory is described by large n. So it's by just these Feynman diagrams. So you might ask, for example, does it mean that the series diverges? Okay, and it has to be resummed.
Convergent, where there's infinite radius or infinite radius, zero radius. Well, there is zero radius of convergent.
Right. Right. So, okay, so I should qualify what you're just right. I should qualify what I'm saying here, and say that that I'm making some strong assumptions here. That the theory is somehow described by this. That the theory is somehow described by this expansion, and that the expansion is unique. Okay, so I'm assuming I'm assuming when I say this implicitly that it converges, and it converges to a unique result. Okay, it's conceivable that that's not the case. Okay, so really turning this into a proof would really require showing that. We really require demonstrating in what sense, or in what sense this large n theory describes a unique result. Okay.
Right?
That's right. It's a slightly different theory, but yes. Okay, so now I'm describing the pure gauge theory now without the glue. No, right, agreed. I agree. You're absolutely right. You're absolutely right. That's right. You're right. No, you're right. And so assuming that's true for the gauge theory is a strong, for the pure gauge theory is a strong assumption. Agreed. Okay, so grant me that for a moment. If you grant me that for a moment, then in that case, that you could rule out this first order possibility. But agreed that you can't really assume that. Okay. Okay. So one's making an assumption beyond. Well, I'm making an assumption that I think people sort of implicitly assumed about large n, but whether it's true or not, whether you can prove that it's true or not, is to question. And it's just right that in the case of n equals 1 at large n, okay, it's clear that that's not the case. Okay. Okay. So I'm just repeating myself here. And again, Misha could repeat his objection, his well taken objection. Okay. Now, there's another feature that is also puzzling if one has these two vacua, which is that one of them is unstable and if one is unstable, then one has amplitudes which behave as e to the minus 1 over m lambda minus m lambda naught cubed, which in terms of n behavior is hard to understand. Okay. In particular, the amplitudes perturbatively behave like is n squared, but again, this is all subject to the same objection, like the perturbative vacuum amplitude. So this should show up in the perturbative expansion. Okay, but as I say, this is a statement of the point above, and it's subject to the same objection. Okay, so pardon me. So another aspect, which is also subject to this objection about diagrams, is that if I consider the theory at small m lambda, where we know it confines, in the far infrared, it scales much less than m lambda, it can be described by an effective theory, effective action written in terms of operators built of f mu nu and ordered in increasing dimension. For confinement, only the lowest dimension operator is relevant. So this minus 1 over 4 g of lambda squared is relevant. F mu nu squared is relevant. At large m lambda, then these statements still hold. So the far infrared theory looks the same. So really what I'm assuming here is not quite the sum of diagrams, but that the degrees of freedom with which I describe the system are the same. So that the degrees of freedom are the a mu a's and not some other thing. Okay, and then again, if that's the case, then confinement follows, because we know the theory confines in the far infrared in the small m lambda limit, okay, and at large m lambda, this statement still holds. Now, you might sort of hope that this expected is perhaps a little strong to this persistent finite n, okay, but one requires the assumption, now questionable, that the largest degrees of freedom are the a mu fields. So I'm learning a little fast here, but just in conclusion, it bears repeating how remarkable it is that one can demonstrate confinement in supersymmetric gauge theories, and that confinement survives if one breaks the supersymmetry a little bit. As a result, one is looking at the question of, is there a phase transition? And as I say, again, I think rather remarkably, one can easily rule out a second order transition. But it's harder to make a definitive statement about a first order transition, and this loophole remains. At large n, such a transition would seem incompatible with standard assumptions. Okay, so it's assumptions which, as said, Misha has questioned rightfully. So the assumption that the theory is somehow uniquely defined by this set of diagrams or by the degrees of freedom of the underlying that appear naively in the perturbation theory. The result at large n at the critical value of m lambda would not be unique. And near this point, amplitudes would be puzzlingly singular. But it is not clear that one can turn this into a proof of confinement. So I say I'm running a little ahead, but that's all I have. So I want to thank you. Alexa, can you wait for Mike?
Oh, of course, yeah. Sorry.
Oh.
Would you mind going? Yeah, this slide. You mentioned that there's a theorem that you can say that there are no massless particles in QCD-like theories with massive constituents.
Right.
I think there's a counterexample to that statement. If you
Okay.
take QCD with one flavor, there has to be a massless Ising point at some negative value of the quark mass. This has to do with the fact that this Baffa-Witten theorem assumes the absence of any sign problems.
The absence of, sorry?
The absence of sign problems, that the functional integral measure is positive definite. This is not necessarily true, and it's in particular not, I don't think it's true in the example you had, because there are Yukawa couplings in supersymmetric field theories. They mess up positivity of the determinant. So I guess that's a comment.
Okay. I will have to think about that. I don't have a quick answer. I think also this the second argument I gave also you may want to question too. Okay, this argument that the effective theory is the same at very large distances, and maybe that would be affected by this positivity question.
Maybe I can ask a question.
Sure.
Very naive question. So you referred to CPN theories, but I think probably most people don't know what they are and how you use them. So can you say maybe a word about that?
Sure. So these are theories where the fields, the bosons, are coordinates of this space called CPN. And I'm not sure I'm going to be able to give a good definition on my feet. This is complex projective space in n dimensions. Actually, I have to think whether it's n or n plus 1. So we have some coordinates I equals 1 to n, and these are identified. These are identified with the point labeled by the zi's is identified with a point lambda zi, where lambda is a complex number. So the zi's are a complex number. And lambda is a complex number. Okay. So this is this space. So the fields live on this space. Such a theory where the fields live on such a space is known as a nonlinear sigma model. Oops. So the fact that this fact, so as a simpler example of this, one can consider just fields, a set of fields which live on a sphere. So some fields chi a, real fields, some chi a squared equals r squared. Okay, and if I take my interactions to be my theory rather to be d mu chi a, but I can replace chi n. So this is say a equals 1 to n. I can replace chi n is square root of 1 minus some chi a equals 1 to n minus 1 squared. Okay, so I can replace the nth field by this sum by this nonlinear combination of other fields. And if I plug that back in the action, okay, and I expand in power, so I left n and r. and I expand in powers of chi over r. Okay, so for a large radius of this sphere, of this n-dimensional sphere, the theory looks interacting, and I can write down a perturbation expansion for it, for example.
And these are scalars though, right?
These are scalars. So the other case I had complex, it's not so different. Complex scalars, the space on which the fields live is different. And in the supersymmetric version, there were fermions that came with it. But the ideas are really sort of the same. The mathematics can be simplified for the mathematics can be simplified by using by introducing Lagrange multipliers and treating them as fields. So rather than doing some complicated expansion of this square root, introducing Lagrange multipliers, treating them as fields. And then, for example, at large n, in this theory and in the CPN theory, one can make statements about the exact solution. So one can do large n, a generalization of this n of the TUFs, wherever it went, and one can solve the theory for large n.
You have other questions? If not, let's thank Michael
Okay,
again.
thank you again.
And we have, there's still, right, it's set up outside the reception,
Great, good.
cookies. A bunch of different ends.
Yes. Yes, there's a number of supersymmetries and
The number of gauge bosons, well, number of mention of the gauge.
number of them, yeah. Of the gauge group.
This, I think, we're going to mail.
That's right, I hope, thank you. I'm sorry to make,
No, it's not a problem, because it's actually, it's pretty heavy.
yeah, I just,
I don't know if you,
I don't think I can manage is the problem.
just to get an idea, pick it up.
Yeah.
We'll ship that out.